Hello again, Physics 100 students and any random people that, I don't know how you would have gotten on this, but I guess maybe you did. It's been 1 week for you, about 4 months for me. Before we start with the lecture, which won't be too dreadfully long, and as you see, not a whole lot of equations, one of which you've seen already, and this one isn't really quite an equation, just an approximation we'll do for this class, because this is an algebra-based class, and we can't do sine and cosine. But before we get to that, I'd like to mention briefly something related to physics that has been occurring to our world in the last month or so, which if you're watching this in early 2016 will make sense. If you're watching this in 2017 or 2018, you'll be like, oh yeah, I kind of remember that. I wonder what was up with that. And if you're watching this in 2014, congratulations on your time machine. That is the extremely warm temperatures we've been experiencing in the month here in December, the 60s and 70s. So what's going on here? How can physics explain this? This is very, very strange. It has something to do with something called El Nino. Now, I know you probably expected me to say something different, that it was global warming. Not quite. It helps a little bit, but El Nino is when the oceans dump a bunch of energy into the atmosphere. It makes the planetary temperatures warmer for about the next year or two. The last time we had this was 1998, which was a year that was much warmer than any of the years before it, and a little bit warmer than the years after. In fact, it took us almost 20 years to get back to the temperatures of 1998 due to global warming. So think of it this way. Think of global warming like a rising tide, and El Nino as a storm surge on that tide. And so that's why we're getting the really warm December temperatures this year, is because of El Nino. That'll go away in a couple years or two, so enjoy it while you can. All right, so today's lecture. Today we're going to talk about sound. Okay, enough of the theatrics. Our objective is to achieve this goal. We're trying to understand sound waves again. We looked at them a little bit last week, but we'll examine waves again. We're going to understand the speed of sound. We're going to explore reflections. We're going to examine refraction very briefly. Then we'll start to understand the energy of sound and what it can do and how we measure that. Then we'll learn, although we won't do the math of that. We'll learn about the natural frequency and resonance, so those two actually go together, and how those can be very bad if you design something improperly, such as, say, a bridge. And then we'll examine some things that Hollywood generally gets wrong, and we'll understand why they get it wrong and why they want to actually get it wrong on purpose. And no, it doesn't have to do with conspiracy theories. All right, so just to wake everyone up at home, which you're probably watching this at 11 o'clock at night, what type of wave is a sound wave? Now last week we learned there are two types of waves, compression waves and transverse waves. At least I call them compression and transverse. I don't use the other word because it makes no sense. All right, so what type of wave is a sound wave? Sound wave is a compression wave. Why? Because to get sound, you have to compress air. For me to make sound, my voice box has to compress the air and then uncompress it, and keep doing this. The number of times my voice box can do this per second gives you the pitch. If I do it very slowly, I get a very low pitch and sound like a whale. And if I do it quickly, I sound like Mickey. So, now there's some side effects of this. That means you actually have to have a material to compress. Now, when the compressed air comes out of my mouth, that compressed air has more pressure, and so it pushes on the air in front of it, which compresses that air, which then pushes the air in front of it, and that wave therefore propagates. But in order to continue to propagate, you have to have material to propagate into. The number of times you compress the air per second is the pitch, which is the frequency. And one way to do this with a speaker is the speaker actually pushes the air in and out like this, and thus creates the compression. So the pitch is how often it vibrates. So if you have two different objects, they will vibrate at different rates, depending upon what they're made out of and how big they are. The sound has to move. The waves have to propagate. And they propagate by pushing the stuff in front of them, and compressing the stuff in front of them. And that takes time. And there's two things that determine how quickly you can do this. The density of the medium, which is partially based on what it's made out of, and the temperature. So the temperature is a measure of how fast the particles move. If the particles move faster, then it's easier to propagate the sound travels faster. Now, why would the density matter? Well, suppose you're putting out the fire 18th century style. You've got a bucket brigade. Now, if the people are separated by large distances, it's very difficult to get the bucket from one person to the next person. But if you have people really close to each other, you can move that bucket pretty quickly. And so when the density is higher, the sound speed tends to be higher. So if you compress air and make the air density higher, then the speed of sound in that air will be higher. And as a result, there's a big difference between the speed of light and the speed of sound. Many of you probably played the game when you were kids of how far away is that lightning strike. You'd see a flash of lightning, you'd count 1,001, 1,002, 1,003, 1,004, 1,005, kaboom! And you would determine how far away the lightning is. For every 4.5 seconds that you count, the lightning is 1 mile away. So if you count 9 seconds, you get a very faint kaboom because it's far away. That's 2 miles away. If you see a flash of light and then half a second later, kaboom, well, that was about 1 block over, maybe 2. And it would probably be very loud. The light, however, gets to you almost instantly because it travels the distance from the Earth to the Moon in almost 1 second. So it gets there very quickly. A mile, it gets there in nanosecond, which is 10 to the minus 9 seconds. So it gets there very quickly. At room temperature, sound typically travels about 340 meters per second, although on a cold day it might travel 330 meters per second. On a very hot day, it might travel 350 meters per second. If you want to measure the time it will take sound to travel from point A to point B, doesn't require a very complicated equation. Just this equation right here, equals VT. And there's no acceleration, so we don't have to have that plus 1/2 AT squared. So just this equation, solve for time, and that gives you the time. If you want to calculate how far the sound will travel in a given time, distance equals VT, and the velocity is fairly a constant here. However, if you move into a different medium, the sound speed changes, the velocity changes. In water, for example, it travels 1,500 meters per second. So if you're in water, you hear the lightning strike before you hear it if you're in land. And it looks like I did this a little bit out of water, which goes to show that the PowerPoints are not here for you, they're here for me. So again, sound is determined by the density and the temperature. But like any other waves, water waves, for example, sound waves can bounce off of objects, they can reflect. And when they reflect, this will create an echo. You'll hear the sound that comes directly at you, and then you'll hear the sound that went past you, hit the object behind you, and comes back. And that's what an echo is. So if you're in a giant cave, you yell, echo, echo, echo. That's, the echoes are the waves that travel further down into the cave and bounced off the walls and come back to you. And they're quieter because they've traveled further and therefore they spread out a bit more. And so when you design a theater or a car, you oftentimes want to take this into account because the sounds will reflect and interact with the other sounds. And sometimes you want those sounds to reflect, sometimes you just plain want them to be absorbed. And so you design your walls to absorb the sounds that you don't want to reflect, and this is called acoustics. Refraction. Now, we're not going to get too deep into refraction here because that involves sines and cosines, so we'll just do the concepts. And I'll kind of give you sort of a pseudo-equation where this equation explains what in is, so there really isn't a whole lot there. Whenever the effective speed of sound or effective speed of light changes in a material or between two different materials, you will get what's called refraction. Now, this Bunyan value n is called the index of refraction. It is a unitless number which tells you the comparison of the speed of the substance to the speed of sound. So for light, for example, I guess I did this for light, the index of refraction equals the speed of light, which is the 3 times 10 to the 8th meters per second, divided by the speed of light in that material. For water, the index is about 1.4. This works for sound waves too, although this is more for light than it is for sound. And so what happens is the light will, because you're traveling at different speed, but you're going to have the same frequency, so the same pitches per second, that means that you're going to get a bending of the light. Again, we're not going to get too far in depth in that. And so what happens is the index times the angle is approximately equal to the index times the angle on the two sides of my chain. So suppose I have 2 layers of air, one's warmer than the other. The warmer one will have a lower index. And so if I take that index times the angle, on the one side, as the light enters that and goes through it, on the other side, it'll equal the index times the angle as well. Now the angles are measured from perpendicular to the, if this is the boundary, it's perpendicular to the boundary. We call this incident. So that means if the index goes up, the angle has to go down. So they're opposite. Whatever the index does, the angle does the opposite. So if I go from air to water, the index increases, and that means the angle has to decrease. I have to have a smaller angle. So the light bends towards the perpendicular. And that's why when you reach into a pool of water or a fish tank to try to grab a fish, you miss because the fish isn't where you think it is because the light has bent. So just to kind of draw a diagram of this, suppose I have my aquarium here, and here's the water, and here's the fish. Here's the tooth. You have a cavity. So the light, you would think that the light would do this. Now this is the perpendicular, so I draw a dotted line for that. But it doesn't. So when it comes out, the angle, and I just realized you can't see this in green. It doesn't erase very well. Not that you can see that. If you watch it, we wipe what appears to be a board that has nothing on it. Okay. Green pin deactivate. All right, here's the black. I tested the green pin beforehand. I couldn't see it on the video. All right, so this dotted line is the angle, and maybe I'll draw you a better fish. Okay. there's my fish. This is the worst fish ever. Maybe he's got a little torsion. Okay, now I've got like a fish submarine. All right, so if everything was water, that line would continue on straight. I'm going to kind of draw a dotted line at this point to represent the actual angle to the fish. But since the index here is smaller, to get these to be approximately equal, this has to be bigger. So my angle has to be bigger, and so that's the angle I actually get. And so when I grab, I think the fish is over here. And so I grab the wrong spot. And this is because of refraction. Now for those who are not algebra based, for example, if you're watching this for my 218 class and I've recommended you watch this, actually this would be 219. If someone's taking 219 or 202 and for some reason are watching this, it's n1 sine theta 1 is equal to n2 sine theta 2. But we don't do thetas. Now this is actually accurate if your angles are very small, but it only works accurately if the angles are very small. But for the intents of this class, we're not doing things too dreadfully accurately, at least especially for this part, so this will work out just fine. But there's a problem. Not from our approximation, but from the actual physics. And that problem has to do with what happens if the angle, since the angle increases going out of the water, what if my angle's too big? So what if I have a very flat, shallow pool, like this, and I have a very, remember all angles are based off of this, if I have a very large angle, well my angle has to get bigger. But if my angle is already, say, 80 degrees, and my angle needs to get 40% bigger, well, that angle will be bigger than 90%. Oops. At bigger than 90%, that means the light doesn't go into the air. It actually goes right back into the water. And what happens is we don't get any refraction, we get reflection off of the surface. And this is called critical. This is called the critical angle. And the angle at which you get total internal reflection, here we go, is based on this physics. Or that's all I can call it. Total internal reflection. Ha, 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 ha. Always sounds like something a supervillain would say. If we get the angle of the water to go into the air to be big enough, we will achieve total internal reflection. That's great. How will that help us defeat the superhero? It won't. Well, maybe he won't be able to see us. All right. So you can't make the supervillain too good because then you can't defeat him without using really weird stuff. Okay. So like, oh, push this button and he goes away. No, I haven't seen it yet. Even if you're watching this in February, I haven't seen it yet. You know what I'm talking about. Anyhow, now a lot of you in this class are going for the medical profession, such as physical therapy or possibly radiography. And there are uses for this in the medical field, lots of uses for this. One of these is ultrasound. So what happens is you send these high-frequency pulses into the body, which is better than X-rays because X-rays have high energy and they can damage cells. Ultrasound cannot, which is why you use ultrasound for babies, because you would never want to use an X-ray for a baby because you would pretty much destroy the baby. Well, maybe not completely destroy it, but big chance of something bad happening. So it reflects differently and refracts differently versus different materials and different densities of materials, and so you can fine-tune it to see as far into the body as you want and see the different types of things, the body such as bones, different types of muscles, ligaments, etc., without actually harming the body itself. So you can make a map of the body without damaging it. And so that's why ultrasound is used quite a bit. And MRI machines do something similar. Energy. Waves have energy. I experienced this a couple months ago, between the last time you saw me. We were in Florida in the ocean, and my little 2-year-old was getting up close enough that some of the waves would hit him. And one of the waves had so much energy that it knocked him down. I freaked out, but he laughed. He thought it was funny. So waves have energy. They have lots of energy. And sound waves have energy too. And we quantify this with something called a decibel level. You've probably heard of decibels. It's an exponential scale, so every 10 decibels is a factor of 10. So 100 decibels is 10 times greater than 90 decibels, and 1/10 as powerful as 110 decibels. In fact, sometimes sound cannot just be heard, but also felt. If you've ever been to a really good fireworks show, I mean a really good one, and they put up the big ones, and you see the big, you see the light, and then a couple seconds later that sound finally gets to you because you're half a mile to a mile away, and you hear the boom. You won't just hear it, you'll actually feel the compression wave of the air pass through your body because it has that much energy even at a mile away. But the concussion from that blast, you can still feel it. So if you're really close to a blast, it could kill you because of the concussion, the compression that compresses your body and internal organs. Okay, I don't want to get too gruesome there. But there's an energy system that called the decibel level. And if the sun has enough energy, it can hurt or destroy your eardrums. If it's stronger, it can break windows. If it's even stronger, it could kill just from the sheer energy of the compression. Although the decibel level has to be quite high to do that. To harm your eardrums, you need about 150. To break windows, you need about 170, 180. And again, remember, each 10 is a factor of 10. So 180 is 1,000 times more powerful than 150. 150 is like right up next to a jet engine. Once you start to get to 200 to 220, that could be lethal to a human being. In fact, nuclear explosions the blast wave is actually just a giant sound wave, in a way. That sound wave can actually push houses almost over, and then of course you get the back end of the wave, which is the decompression part of the wave, and then the house gets sucked the other way, and then pushed back the other way. And so that's why things tend to break, is because they're pushed one way, and then they're pushed the other way, and then they're pushed the other way, and that just snaps the heck out of everything. This leads us to something called natural frequency. Now, remember for the last video, which for you was a week, or if you're cram sessioning this an hour ago, or in my case, 4 months ago, I did the waves, and you can see that if I did it at a very specific rate, I get these standing waves. And that has to do with natural frequency. The natural frequency of an object is determined by the time it takes the pulse to travel down the object and back. If the object is bigger, it takes longer to do that. So for example, a little tiny bell goes ting, ting, ting because it doesn't take very much time for the sound wave to travel back and forth through the bell. If you have a very large bell, it goes bong, 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 because it takes a very long time for the sound waves to travel back and forth through that bell. And so the natural frequency is a frequency which it will naturally vibrate. It also depends upon material. Different materials have different sound speeds and therefore will have a different frequency. So if you have plastic versus metal, I don't know offhand which one has a faster frequency, probably the metal, or faster speed, probably the metal. And so if that's the case, the metal, if you have a metal that has a higher sound speed than the plastic and made of the same size, the metal will have a higher pitch than the plastic. Now, if you vibrate something at its natural frequency, very bad things could possibly happen. Not guaranteed, but it's possible. For example, if a singer sings into a glass with enough power at its natural frequency, you can break the glass. Now, the reason why you can do this is because of constructive interference. I'll just leave this up for a moment. As the wave goes down and back, if I start the next wave at the same phase, as it comes back, the two waves will add together and create a bigger wave. And so what will happen is the vibration will get larger and larger in amplitude over time as I continue to pump energy into the object. So unless the object has a way to get rid of this energy, the amplitude will build up and build up and build up. And at some point, the vibration will be so big that it will break the object. So, hypothetically, if there was no way to get rid of the energy, if I pushed the wall at its resonance frequency, I would make the entire building vibrate. And the vibrations would get bigger and bigger with time until the entire building would fall down. Now, luckily for us, there is a way to dissipate the energy. So that means that Tesla's building-destroying machine could get the building to vibrate, maybe, but it probably wouldn't destroy it. And this leads us to something called catastrophic resonance. If the resonance is strong enough and amplified enough and given over a longer time, it doesn't have a way to dissipate the energy builds and builds and builds, this can be a very bad thing. It can destroy your glass or an entire bridge. I am from the state of Washington originally, and in my state we have a bridge that back in the 30s got the nickname Galloping Gertie. This is a bridge that links Tacoma, Washington with Gig Harbor, Washington across Puget Sound. In 1940, a high wind came by which made the bridge sway at its natural frequency, and the wind was doing the pushing. The swaying got stronger and stronger and worse. Now, it took a lot of time for this to occur to build up this amount of amplitude. And so the people on the bridge realized something was wrong. Most of them got off of the bridge. No people or animals were harmed because one person made a last-second heroic effort to save their poor dog. One car was destroyed. But it destroyed the bridge. And then the engineers realized that they had to build the bridge to withstand the winds and not sway. So they had to rebuild the bridge, and there's a new bridge there today. Well, new world. And so this is one example of catastrophic resonance. Now, this took very high speed, very powerful winds to accomplish. Could you do this with a piston? A small piston that you put on the side of the bridge to push the bridge at its resonance frequency. Would that, we're not there yet, would that destroy my bridge? Well, it turns out the answer, this has actually been tested by Mythbusters, is no, it does not. Although Mythbusters didn't understand why this didn't work. They did get the entire bridge to vibrate slightly, but it didn't destroy the bridge. Why not? Well, it turns out there is a way to dissipate the energy. As things vibrate, they rub together. As they rub together, friction converts that vibration energy into heat energy. And so you end up heating the bridge slightly. And so the more you vibrate the bridge, the more friction there will be. At some point, the friction will dissipate the energy at the same rate that you're pumping energy in, and at that point, the amplitude will stay constant and no longer increase. You'll have what we call equilibrium. And so don't worry, you cannot destroy a bridge with a little piston. It takes a lot of wind to do so, although most bridges today are designed so that even the wind won't even be able to do it. So it would take quite a bit to destroy most bridges today, thankfully. And that's why even if at residence, if you see your residence into a glass at home and you try this like they did on also Mythbusters, you probably won't break the glass because you probably won't have enough focused power into the glass to increase its amplitude enough to be able to destroy it, because if you don't have enough power, the friction at some point will equalize the power you're putting into it. It will vibrate, but it won't vibrate enough to actually be destroyed, even at the resonance frequency. So you have to have a pretty powerful set of lungs to be able to do it, as well as enough control of your voice to be able to hit that pitch perfectly. All right, now on to stupid stuff that Hollywood does. I could probably give 10 lectures on this and not barely scrape the surface, but we're just going to focus on sound today. All right, a spaceship explodes in space. What happens? Well, you see, usually this fireball go like this, like it's a pancake. Well, in space it would actually be spherical. Oops. And usually you'll hear it go boom, just because it's weird to see an explosion and no sound. So they tend to cater to their audience for theatric effect. In space, if you scream in space, I cannot hear you unless you have a radio. Then I can hear you unless I turn the radio off. Then I can't hear you. Most oftentimes in sci-fi movies, you'll see the spacecraft go by you. It'll make some kind of noise. Even though there is no sound in space, because there's nothing to compress. The sound speed would go to 0. So why does Hollywood do this? Why does it make a whoosh or a vroom noise through space when there would clearly be no sound? Well, this is because at some point in time, they did a sample audience without sound, like it should be, and the audience was confused because they didn't know if the object was moving or not if it didn't make sound. So they put the sound in so that the audience knows that the object is moving. Again, it's for theatrical effect. So they break the laws of physics for theatrical effect. Because the audience wouldn't know what's going on, at least that's their hypotheses, if they didn't include the sound. You wouldn't be able to tell if that spacecraft in the distance that you're seeing is moving away or if it's just sitting there in dead water, unless it's making a whoosh sound. So that's why they put in the sound, for theatrical effect. So to wrap up, I told you this would be kind of a short one. Sound is a compression wave, and just like all the waves, it bases properties. It does not travel in space. It has energy and can destroy things, especially if you're in resonance. Sound can reflect and refract. I should put refract in there. If it enters a region where the sound speed changes. By the way, that means that if you do sonar, which is sound, because there's different densities and temperatures of water, it will refract, and there are actually areas in the ocean where you can't see things. So submarines can hide in those areas from sonar. So sub-pilots will know where those are. Good hiding spots. And that is all for this lecture. I will see you all next week, or maybe for cramming all of them into one night. I will see you in 5 minutes. Or 5 seconds, I suppose.